So I'm really pleased to introduce Daniel Creed, who's our new neighbor, having just started one semester ago as assistant professor at CMU. Daniel did his PhD at Berkeley with Dan Klein, and then also postdoc at UW Settlemyre. And he's done internships at all of the big places, working with excellent people. And even before grad school, he did an internship with one of the best people, Kevin. We got to have dinner with him last night at the reunion. Daniel, I should also mention, for those of you who are currently grad students, that while a grad student, Daniel, in addition to getting fellowships like NDSCG and the Google PhD Fellowship, also won awards as an outstanding teacher and an outstanding reviewer. So doing well by doing good. You should aim for those two. His work has ranged over a number of topics. For example, we've worked on things like parsing from time to time, but most of his papers are pretty well described by the title of his talk. So he's looked from many angles at ways in which language utterances can be seen as moves in a game, and how that game is played over time, and how it's affected by conventions, and how it's affected by context, and how it's affected by the states of the individual players and how they're using that each other. So if you hadn't already seen it a couple of months ago, he and some colleagues posted a survey article on Archive, which is a really good summary of the different directions that Pat's work in this area has looked at. So I will stop talking because he's got a lot to say.
Thanks. Yeah, thank you for the really kind intro, and yeah, for the motivation for the work too. But like Jason said, I'll be talking about how we can try to model language as like a strategic and a contextual action, and how modeling language in this way will let us help NLP systems improve in their interactions with people on task-oriented domains, kind of across a range of diverse settings. So the motivation for this work is really building natural language interfaces, like systems that can perform useful tasks for people that you can talk to in natural language. And sci-fi has kind of always been a source of like the aspirational goals that people have for these kinds of systems. So here's an example from 10 years ago from the movie Her. And it's a dialogue between a digital agent named Samantha and a man, Theodore. And it goes, let's start with your emails. You have several thousand emails regarding LA Weekly, but it looks like you haven't worked there in many years. And the man says, oh yeah, I guess I was saving those because in some of them, I thought I might have written some funny stuff. And the agent says, yeah, there are some funny ones. I'd say there are about 86 that we should save. We can delete the rest. So this is kind of the dream for NLP, right? It's a system that just seamlessly interacts with you and figures out your goals and helps you to carry them out. This was made for my job talk, and I used to say that we're a long ways off from this, but I had to replace the failure examples with an example from ChatGPT, and some things have really improved. So we can say, please help me organize my emails, and the system's able to give this very knowledgeable and fluent and persuasive response. Sure, here's some tips for organizing your emails, and it produces this long, like 500-word response with all the different things you can do to manage email overload. But really what I want the system to do in this case is to like actually, organize my emails for me. And the system's just a text-based AI that's designed by OpenAI, and so it can't do this. So I think these systems have a lot of capabilities. They're even starting to have some kind of pragmatic capabilities, which we'll touch on a little bit later. But we really want to be able to tie language up to a variety of range of contexts in order to have it do useful stuff for us. So tying language to text, ChatGPT is a nice example of that. We've had big advances in language modeling, semantics, question answering. So it's able to tell me that Southwest is the airline that I could use to get nonstop from Pittsburgh to Baltimore. Very convenient. I recommend it. Come visit us in Pittsburgh sometime. But we also want to tie language to, the physical world to go beyond text. So if we want a system to be able to carry out high-level commands from a person in a complex environment, we need to ground language. So we have to tie it to kind of extra linguistic things that we directly see in the world. But we also want to allow interactions between a system and a person. And to do this, we'll often have to tie language to the intents that people had when they produced it and the effects that language has on other people. So if I say my neck hurts to my smartwatch, it's not just a literal statement about my neck, right? It's kind of an implicit request for help. And the system should model the pragmatics of language, kind of the way that language is used in context to achieve goals, and figure out that the person's implicitly asking in this way. So I'm going to be talking today about grounding and pragmatics, kind of how does context affect language in task-oriented settings. So here's an example of both grounding and pragmatics. So grounding is kind of about the literal meaning of language in the world. And if you're a self-driving car and you're sitting on the street and someone says to you, stop at the second car, you should be able to figure out that they probably mean this car here. But sometimes language is more ambiguous. And if someone says stop at the car, there's a bunch of different cars here. Which one do they mean? So if you think about it for a second, how many people would say this car here? So a few folks. How about this car? So there's some variation, and it's not, it's ambiguous. It's not totally clear, but most people choose this car here. And there's a lot of ways you can derive this. There's salience, there's conventionalization, but a big part of it can be explained. And we'll see how in a second by reasoning about alternatives, that if the person had meant a different car, like the second one, they probably would have been more specific. So to build pragmatic systems, we can take a clue from work on the purpose of communication. So here's a quote from the philosopher J.L. Austin, where he describes how language and action are tied together. So saying something will often produce certain consequential effects upon the feelings, thoughts, or actions of the audience. And Paul Grice carries this further in some really foundational work where he says, our talk exchanges are cooperative efforts. And one of my aims is to see talking as purposive, indeed rational behavior. So Grice and those who have followed him show how you can derive a lot of the pragmatic aspects of language by assuming that people are agents that are trying to cooperatively figure out what each other means by reasoning about each other. And so kind of the motivation that you can distill from all of this is that language is an act that people take to produce effects on other people and through that on the world. So how do we operationalize this view? I'll talk about a couple projects that all take basically a game theoretic view, like Jason mentioned, on language production. So they see language generation on the left and interpretation on the right as a game between speaker and listener agents. And these are called reference games. So I'll show generation first. So there's a reference, something in the world that the speaker is trying to get across to the listener. And the speaker is going to have a choice of different things they can say to try to get this goal across. So if I show two different choices they can either make this move of saying stop at the car or stop at the second car. They could maybe say other things too, but they're going to hand that off to a listener who's then going to choose how to respond. If the listener is kind of a simple one that just takes everything literally and we say stop at the car, we don't know which car the listener is likely to choose. Whereas if we're more specific and say stop at the second car, the listener has a higher chance of getting it right. So to be effective in this game, the listener should choose to say something like that. So we can also use reasoning for instruction interpretation. If we get this ambiguous instruction, stop at the car, the listener can reason about the speaker, reasoning about the listener, and try to figure out what goal might the speaker have had in mind that made them say what they did rather than something else. So they had some goal in mind. They chose language to try to achieve that goal. And we can figure since they didn't choose a more specific alternative, they might have meant this car here. So we'll use this kind of joint reasoning between speakers and listeners to improve the performance of systems on a range of language grounding tasks. We'll build speaker models that produce language in context and listener models that interpret it. And we'll train these models on data from people so that they roughly imitate people's behavior. And then we'll show that we can use each type of model in simulation to help the other type of model so that speakers help listeners and listeners help speakers. And we'll find that if you plan against a simulated model of a person, it can often help you do better when you're collaborating with actual people. So this is kind of a high-level framework. It can be instantiated in a lot of different ways. We'll start off with using pragmatics for grounded instruction following, and then I'll talk briefly about some interactive settings, including preference learning, and then work that I did with the fair diplomacy team, where we built an agent that plays the board and negotiation game diplomacy. So we'll look at using pragmatics for grounded instruction generation and interpretation first. So it's sort of a complex reference game setting where reference are now paths that you take through the world. And we'll find that pragmatic reasoning of the kind that I sketched out a slide or two ago will help to make models more informative, help them to lie or hallucinate less, and let you learn from noisy data from people and outperform the people who you train the models on. So the setting that I'll use to kind of illustrate this is one that we looked at called vision and language navigation. So it's generating and following instructions through scans of real world buildings. So people were shown a path through an environment like this, and they write an instruction like turn left, like we just did. Take a right at, you can see the table here, then take a left at the painting, and take your first right. Wait next to the exercise equipment. So the environment here, it's basically an indoor street view. There's a graph of connected points within these houses. These houses are like from this company called Matterport that has basically people looking to sell really nice houses, kind of set up panoramic cameras inside so that people don't actually have to do tours of the buildings. But you have these panoramic images that are all connected in this navigation graph. And you're gonna like have a virtual agent that moves around basically in the street view setting and tries to interpret instructions by conditioning on the images that it sees along the way. So there's two tasks that we're interested in here. First, there's the interpretation task. So you get an instruction and you start at an initial in the environment and you get this visual observation and you predict discrete actions that you would take to move you around in this environment. And moving updates what the agent can see, and it will like predict, for example, to turn right and then go into the living room and then walk forward onto the rug and predict to stop. And in this case, it would get it correct because it stops at the end location that the instruction was intended to get it to. So that was the interpretation task, but we're also interested in the language generation task. So given this input route, the sequence of visual observations and the actions that move you from one to the other output an instruction that someone else could carry out correctly, just like we just saw. So I'll talk about the, question.
Can you backtrack if you feel like
You can implicitly backtrack. So you can, you're free to move to any location that is connected to one that you're currently at. The supervised data for this doesn't use backtracking. And that's actually an artifact of the way in a lot of these data sets that the routes were produced. But obviously the models can make mistakes. And so people have kind of like exposure bias, dynamic oracle-like ways of training using either like an actual oracle or reinforcement learning that help it to learn to recover from errors. Yeah. Any other questions on the setup? Okay, so I'll talk briefly, kind of at a high level about the building blocks that we use for this task, but the approaches that we try to use are basically model agnostic. We require that the models are probabilistic. So we have a listener model, which does this interpretation task. It takes in an instruction, it outputs a sequence of actions that constitute a route along with observations. And so it'll be a distribution over those actions, a distribution over possible routes. We also have the speaker model, which performs the inverse, the generation task. So condition on a route, produce a distribution over sequences of words, over instructions. Yeah, question?
What is the speaker model for you?
So the speaker model for us will be a model that produces these instructions that we train on all of the instructions that were written by people on this task. So it's kind of a model, maybe at the population level, of how people would produce language that, at least for the population of annotators that were collected for this data set, of how they would produce language. So those are the models at a high level, but using a probabilistic model is important because we want to represent uncertainty in how someone might carry out an instruction. And later on, this will let us reason about alternative routes and alternative instructions. So, yeah.
When you started motivating this about how the listener in turn might reason about what the speaker was thinking.
Mhm.
So I was expecting that you might have in the conditioning R comma P hat of P hat L, or in for the listener I comma P hat R. Meaning that's your best estimate of what the speaker. So are you going to get to that now or later?
Yeah, I'll get to it later. So the framework that we use is based on what the rational speech acts framework, which starts off with models that don't reason, that just kind of have like a literal semantics built in. And the models that I'm presenting here are designed kind of to implement that literal semantics. The reasoning comes when you combine the models together in one of a couple frameworks that I probably won't have enough detail to kind of be satisfying in the talk, but yeah, there's different ways you can do it. One's kind of using game theory, one's using like Bayesian reasoning that combines the two models. But I won't go into details about the base models, partly because they're older. We did this work in 2018 for this paper, but you know they're just sequence to sequence neural models. So your listener model encodes an instruction and then outputs actions one at a time using a neural decoder, and that decoder gets access to the instruction, but it also gets access to the visual observations, and you encode that with a pre-trained vision model and you output your actions, which update your location in the environment, which update the inputs to the decoders, and so on. So that's the listener model. The speaker model that we make is basically just the inverse of this. We encode the sequence of visual observations and actions, and then we output words one at a time using a decoder that attends to that sequence.
And for the speaker, these are the image frames of the intended route.
That's right. Yeah. Yeah. So you get the image frames and you basically augment those with a discrete action that was taken, you encode it, and you run, bidirectional encoder over that. Yeah. So we have these base listener and speaker models, and now we'll talk about at a high level the reasoning procedure that we use to combine the two together.
Right, just a quick question.
Yeah.
Where does the speaker model know the goal?
The speaker model implicitly gets the goal as the last visual observation in the sequence.
Oh, I see. The speaker model has to look ahead. It's not doing incremental.
It's not doing incremental. Yeah. So we do bidirectional encoding of the full route. Yeah. Great questions from everyone. Okay, so we have these models and we'll train the models on data from people, and we'll use a variety of existing data sets. One of them is this data set, it's called Room to Room, that has all the examples that I've been showing so far. But all the data sets were collected by, you have a route through an environment, you show it to a human annotator, and they write an instruction for it. So kind of the process that I described a bit ago. And we'll use this data to train our speaker models to maximize the likelihood of instructions given routes, and our listener model to maximize the likelihood of routes given instructions. And we'll use the same data to train both the listener and the speaker models. But we'll find that even though the base models are trained to imitate people's behavior, they'll still make some mistakes that we'll find a procedure that combines the two together, a simple procedure, can improve upon. So I'll sketch out the pragmatic generation procedure, and kind of the details of this have varied from project to project, but the high level approach is typically the same, where you have a thing that you want to describe, and you have a speaker model, which is going to propose different possible descriptions of it in language. So you can get these through a variety of means, like through doing beam search or sampling. These days with the models we have, sampling is typically pretty good. It gets you a diverse range of things to choose from. I'm showing 2 examples here, but in practice we'll use like 10 or 40 or 100. So you take each of these and you evaluate them using a listener model to see what's the probability that your listener model would be likely to carry out this intended sequence of actions in context conditioned on this instruction. So we go through each of these instructions in turn, and we evaluate the probability by feeding them as fixed input to this listener model for a fixed output. So this listener model has a somewhat lower probability, 0.4, of carrying out the instruction correctly, because the instruction is more ambiguous about where to stop. It doesn't say stop once you are on the rug, whereas this other instruction has a higher probability, 0.8. So after going through all of these, we choose one that has a high probability, or potentially also combine in the score of the speaker model that proposes. So it's basically just a re-ranking procedure. that uses this kind of like, you can also think of it as like being a noisy channel model or cycle consistency, using a model that goes in this forward direction and an interpretation model also. So let's look at how well this improves, if it does, the quality of instructions produced by these systems. So I'm showing results across a range of domains, including navigation settings, but also some kind of like semantic parsing like data sets. I'll have some examples from those in a second. But the dotted lines here are the performance of people at following instructions written by other people, so mturk annotators, on all of these data sets. And the instructions that were written, which are the ones we use to train our models, are kind of varying qualities. And people are actually only able to carry them out effectively between like 66 and 80% of the time. So they're mechanical Turk workers, and both due to ambiguity in the environments and maybe people kind of going fast, there's room for improvement. But the base models that we trained, which were state of the art at the time we did this work, there's a big gap in performance at how easy the instructions they write are to interpret correctly. But if we add in this procedure that uses the listener to re-rank to produce this pragmatic speaker, we get a really big improvement across domains. And this is interesting because this approach doesn't use any separate data. It just has these two models that give different views on the data and combines them together. And in some settings, we actually produce instructions that are easier to follow correctly than ones written by people. I'll have some examples that kind of show an intuition for why that might be true in a second. It's important to note here that while blue is a good evaluation metric in other domains, it's not a good evaluation metric for instructions because you could have one word missing that totally throws off the semantics of your instruction, but is very similar at the surface level.
Can I ask a question?
Yeah.
So because a human is trying to follow these instructions, it sort of makes it difficult for me to understand what's going on here. And part of it is that the human has a model of the speaker.
Yeah.
And so in some sense, what I'm thinking, I'm intrigued by the fact that on Tangram, even the base speaker is that good, because the intent of the speaker might be much more clear in a constrained setting like Tangram, that we know what you need to build or something.
Yeah.
Whereas I don't know these other data sets. I mean, I'm thinking that is alchemy, for example, the least obvious to guess what the speaker might be trying to do or something? Do you have a sense for why?
Yeah, I think some of the examples that I show in a second may give a better sense for that. One thing to point out is that tangrams is kind of different than the convention formation setting of tangrams. It's kind of an unfortunate name collision. It's sort of, we'll see an example from that too.
So it's not the actual thing.
It's kind of moving, they're tangram shapes, but you kind of move them around. Okay. And there's actually, it's goal direct. Yeah, you're just moving them around. You're not assembling them. And you're actually not using the abstract names to refer to them. Okay. Yeah. So it's a little bit different, but they're basically all sort of like object manipulation. The three over there are basically object manipulation settings.
But there is this confound though, that the listener in this case has a model of the speaker that you don't, that is either match or not quite match. Right.
Yeah, yeah. So yeah, we can talk a little bit more later if we have time about, kind of these models are trained on pragmatic data from people. And so it's kind of interesting that this procedure still improves over them. And I think it's due to limitations of the base models. But yeah, so here's an example where, so this is one from the alchemy setting, and they're multi-step instructions, or routes, but I'm just showing one step here where, this purple chemical beaker on the left had the chemical poured out. So the base speaker describes this as throw out the purple chemical, which is true, but it's kind of like not sufficiently informative that a person could carry it out correctly, right? Whereas our pragmatic speaker considers that, but also considers and chooses this other one, throw out the first purple chemical, because that really increases the probability of the listener model getting it correct. Which is, similar to the instruction that was written by a person here, remove all the purple chemical from the beaker on the far left. So the interesting thing here is if you get, if you're looking at this top row and you get this instruction, it's a bad instruction. It's ambiguous. You don't know which beaker to choose. And so it's clearly underinformative. We did qualitative evaluations and people realized that. So without knowing what the correct goal was, people realized that the pragmatic speaker was a lot more informative. They felt the task was easier and they were more confident. So that's in this setting, but in other settings, the behavior is a little bit different. The pragmatic speaker also makes instructions a lot easier to follow correctly, but people often don't realize that they're having a higher chance of being correct. So here's an example from Tangram. So we have these shapes that are like, deleted or added back. And so first, this shape on the right is removed, and all, both models and the person basically say, take away that last figure. When we get to the second one, things are a little bit more interesting. So the base speaker says, add it back, which sounds fine, but it's not specific about where it should be added back. And a person carrying this out might choose to add it back in the same position. So the pragmatic speaker specifies it should be added back in a different position than it was taken away from. But interestingly, the person who annotated this made a similar mistake to this base speaker model. So the pragmatic speaker in the settings actually performing a bit better. And I think this is still relevant these days because natural language generation should be about producing language that has the effect that you want on a person, not necessarily just about making language that looks good. So we found that the same approach of, have a speaker and a listener model that kind of go opposite directions on a task improves performance across a range of domains. So in all of them, we'll construct a listener that's appropriate for the task and have the generation system use this listener to choose between possible outputs. So for document summarization, your listener is going to try to reconstruct parts of the input document from the summary that you produced. For code generation, you're going to be your speaker model is going to condition on the stock string and try to write a function that implements it. The listener model is going to try to produce a doc string that summarizes the function. And for image captioning, you're going to try to identify the correct image from a set of possible distractor images, some of which could potentially be weighted because we only get the target image in standard captioning. But in all of these, we find that the same re-ranking performance improves upon at the time that we did the work state-of-the-art models. So we have this really simple procedure which simulates how language might be interpreted. We find that it makes generated language more informative in context. And reasoning strengthens models and sometimes allows them to outperform the noisy data or ambiguous data that they were trained on. So that's generation. We can also invert this process to do the interpretation task pragmatically, which your question touched on a bit. So here, a listener can reason about what might have made a speaker say what they did rather than something else, which is kind of the process that you go through, like when I showed you that example of the cars and you picked out the correct one. So we'll use the same base speaker and listener models that I showed before, and essentially the same generated re-rank procedure. So we have this instruction that we want to interpret, and we'll show it to a listener model. And we want to evaluate under a model of the speaker, what route would have been likely to make the speaker produce this observed instruction rather than alternatives. So we'll produce some different candidate. These are, there's a lot, this is the generative model, so there's a lot of other things that it could be producing here. I'm just kind of illustrating one, but we don't actually generate them, they're just implicit. But we go through different possible inputs to the speaker proposed by the listener. And the way you get these is domain dependent. In this navigation setting, we have to do kind of like a structured, you could sample or do a structured search through the environment, but we'll go through each route in turn and plug them in as inputs to the speaker model. So this first route, which stops on the rug, has a lower probability, 0.1 of this instruction, because a lot of the probability mass is taken up by other things that are more specific. But we'll associate that probability with this route and then move on to another one. This route, which stops earlier, doesn't stop on the rug, has a relatively higher probability, 0.2, because this more specific instruction is incorrect in this case. So after we go through all of the routes, we'll choose the route that has the highest probability. So you can also interpret this as Bayesian inference with a uniform posterior over routes. Or if you combine scores of the listener and speaker, it's basically a weighted mutual information objective, trying to make sure all the info is the same in your input and your output. But we find that this also improves, particularly in settings where there's a lot of ambiguity in instructions. So for this navigation task, the past state of the art at the time we did this work got about 25% accuracy at getting to the correct end destination that these human instructions were supposed to describe. We made some improvements to their base listener model that got us to 36. And then this re-ranking procedure using our speaker model gets to 54%. But to give you just kind of a qualitative example here, so here's an instruction and the route produced by our base listener model, where walk past hall table. It doesn't say which way to walk, but the model chooses to go left. Walk into the bedroom. These houses are all kind of nice. There's 3 bedrooms on this floor. The model chooses this one here. Make a left at the table clock. There's no table clock here, but wait at the bathroom door threshold. The model kind of recovers, does the best that it can. This isn't the correct route that the person had in mind. So the correct route actually goes this other direction past the hall table, walks into this other bedroom, makes a left at, you can see the table clock here, and then waits correctly at this, this bathroom door threshold. So basically the takeaway here is that simulating why a speaker said what they did can help resolve ambiguity in instructions. Okay. Yeah, question.
Some pragmatic frameworks assume they're to be lazy, right? Like,
Yeah.
Want to say as much as possible, but not.
Yeah.
I wonder how would that fit here?
Yeah, it's a great question. So the general framework that we're adopting and applying to these problems, the RSA framework, allows like modeling explicit utterance costs as part of the generation process. We have not done that in any of the stuff that I've done so far. And part of the reason for that is that these models, partly because of the data that they're trained on, which tends to be, kind of minimally sufficient utterances, potentially also partly because of, like the length biases of generative neural models do tend to produce shorter utterances. So just by finding things that have high probability under the proposal models, we kind of don't need to bake that term in. I think that's going to be really important when you move to other settings where people could like choose the interaction modality they use with the system. So like if you're choosing to, like in a code setting, like make an edit to the code versus like, write text about it, some of those are going to be higher cost than others, and reasoning about that could potentially help you more. But yeah. Any other questions? Okay, so next we'll look at an interactive setting where we learn info about people's preferences from the language that they use. And this is work that was led by Jesse Lin, who's a PhD student at Berkeley. So imagine that you're a flight booking agent and someone comes to you with a request to get from Pittsburgh to Baltimore. And you give them back a set of possible flights that satisfy their constraints. And they give you kind of an instruction that picks out one of these flights. So I'd like the JetBlue flight. Okay, great. That's unambiguous. We can easily pick out the JetBlue flight here. But what we'd really like to do is to have this agent be able to act on behalf of the person in other settings without as much direct supervision from the person. So if I get some other sets of flights and I kind of know what types of flights the person prefers, I may not need language supervision or as much language supervision from them to act on their behalf. And one way to do this is to try to infer the general preferences that people have from what they say in particular contexts. So one way to do this that's been developed in robotics and human-robot interaction is by modeling people's preferences as reward functions. So if we assume that we have sort of a set of features on flights, for example, like the carrier, how long the stops are, the prices, we could represent people as having, some value that they assign to each of those features, like a scalar, positive or negative. And then we can get a reward for each flight by, just a linear combination of this reward parameters, their preference function, and the features. So the question is, how can we make, and this will be obviously a simplifying assumption, but it's the one that we'll work with to make the inference procedures tractable. But the question that we'll deal with is, how can we make inferences about people's preferences, which are context independent, or at least we'll assume that they are, from the way that they use language in a particular context? So the person gave this description, which unambiguously identifies JetBlue, but there's other things that they could have said here. So for example, they could have said, I'd like the expensive flight, which still refers to the same flight here. So maybe they prefer kind of like first class or fancy accommodations. And both of these utterances refer to the same flight, but since people chose different ways to express them, it might reveal different things about what they prefer. So that's the key idea, that the way people refer to the actions they want might leak some information about their general preferences that we could exploit. And this could help us to kind of generalize and act on behalf of people in longer term settings. So the setting we'll deal with here is going to be based on reference games, like the settings that we looked at before. So you have language that identifies one from a set of possible options. But here we're going to be dealing with a sequence of reference games. And we'll represent these, if you've seen MDPs, as MDPs. If not, don't worry about it. It's actually a contextual bandit setting. But basically, you're going to have these contexts, each one of which is a set of flights, each one of which has some features on flights. You'll have this preference function that underlies all of these contexts. And so that preference function is going to make one flight optimal in each context. And you're also going to have utterances for some of these contexts that identify that optimal flight to the person. So we'll be explicitly Bayesian here. We'll have a pragmatic listener, which is going to be built on a speaker model. So before I kind of gave you a bottom-up presentation, this one's going to be top-down. So our pragmatic listener is going to parameterize a distribution over these reward functions, these linear preference vectors. And we're going to derive that from a speaker model, which produces utterances in particular contexts, M, also conditioned on these preference vectors. So how do we define the speaker? We need to have something that's both context dependent, so this particular M, but also context independent, just the reward generally. And we'll model the speakers as choosing their utterances using two components. So one component is based on getting a listener to choose the correct action, like choose the correct flight just from this set. And the other component is to kind of give a more context independent description of their reward function generally. So we'll just do a weighted interpolation of these two functions, which will make the inference and the modeling more tractable. But as a thought experiment, let's think about what different values of this trade-off parameter might look like. So if I'm a speaker who's trying to induce the correct action in a listener for one particular set of flights, I could just say like flight one, or the flight that costs $42 or something like that. Whereas if I'm trying to just convey my rewards and I don't care about the flights at all, I might kind of just like list off the features and the values that I have for them. Of course, these are both pretty artificial. And if you have natural language, it might look something more like this. Like, I like JetBlue, but not too expensive and definitely not too many stops. There's still some uncertainty about what the relative weights of the features are, but you at least get the polarities. Or closer to this only action side, you might say the JetBlue flight, which picks out one like we saw before. So this is a little bit more like nearsighted, right? It's kind of just describing what you want right now. Whereas over on the right side is more farsighted, saying kind of like what you want generally. But of course, people are really going to have a mix of these. There's probably going to be like, speaker specific or context specific preferences, but we'll just set a population level parameter of 0.5 in this mixture. So we've seen this equation before. It's this speaker model that's a combination of these two base speaker models, one nearsighted, one farsighted, actions versus rewards. And just to kind of like give you, present these in a different way, there's this action speaker, which models, you have preferences, which give you your optimal flight in a particular context. And then you're going to describe that flight using language. So the language is conditionally independent of the flight, or conditionally independent of the reward given the flights. So that's the first component, the nearsighted speaker. We also have this farsighted speaker, which is just going to map directly from the reward to the language. And we'll combine those two together to get our speaker model, and then do Bayesian inversion of that to get our listener model. And we're implicitly assuming that there's a uniform prior over rewards. So speakers are going to choose utterances that produce the right actions in a listener and describe the reward. And listeners are going to infer rewards that would make a speaker pick out the actions they want to get across to the listener. Yeah, question?
So, sorry, maybe I'm remembering the formula wrong. But this is a mixture model rather than a product model, right?
Yes, because we're adding the probabilities together rather than multiplying. Is that the difference?
That's the difference. Yeah.
Right.
So I'm wondering whether your informal description is actually accurate. You're saying that they have utterances that are doing both. And it seems like any individual utterance will do one or the other, but it might not have any utterances that actually accomplish both at once.
Yeah, that's a good point. I don't know if we experimented with a product model for this. It'd be interesting to try it and see. Yeah, we'll see some examples of utterances also in a bit. Yeah, so we collected data for this basically by having people kind of, role play, do a Wizard of Oz version of the setting that I showed you. So it's this task. We had two Turkers get paired up. We gave one Turker a parameter vector, this reward function. It's simplified. It's not, like really precise scalar values, but we showed them what flight would be optimal. This was really hard there's still room for improvement, but it was really hard to kind of like set this up in a way that was tractable for people to understand and also felt natural. But so it's a reference game. This person is trying to get this flight across to the other person. But once they produce this utterance, they know the other person is going to have to go ahead and go through a set of other reference games and try to pick out the optimal flight based on this instruction here. And this person goes as far as they can. They kind of get bonus based on how far they get. Both people do. But if they get it wrong, or if they want to ask for clarification, they can at any point in time. And then we'll get a new utterance for that context set. So we get kind of a mixture of language of different types. So some of this is like, pretty reward descriptive, others pretty trajectory descriptive. It'd be interesting to like try out different, more sophisticated modeling on it. But even when you get kind of like full descriptions of the reward, like this one here, I need a flight with any airline and so on, there's still uncertainty about the trade-offs in the language that you have. So I think there's room to do interesting modeling on this data set that Jesse built. So we'll build listener models for this task, implemented using the thing that I just showed you, and we'll evaluate them on held out accuracy. So we want to see how often can the system correctly identify the optimal flight across a large number of synthetically generated held out contexts. And we'll basically, have the setup be the same as the human experiments. We'll show the system a number of contexts with utterances for them that all describe the same reward. So we'll basically ablate the components of our mixture model. So if we just have a nearsighted model that only that doesn't model how speakers produce language based on the reward, but just describes the flight that was chosen, we get this performance. If we only have the reward component, which would be more like a kind of traditional instruction following or inverse RL model, it gets an improvement, but ours, which combines both together, improves further. But the interesting thing is how performance changes over the course of multiple interactions. So while this combined model is always better, or at least as good as either model independently, there's a large gap between the importance of modeling rewards, comparing this action only to the combined at the beginning. So, language can give you a lot of information about preferences initially, but then as you continue over the course of time, this gap closes and you get a bigger gap between this nearsighted and the full model, because kind of the choices that people make about flights give you more fine-grained info that lets you kind of narrow down your reward more precisely. So the takeaways here are that language is kind of ambiguous at multiple levels of abstraction, and we can extend reference games to study this. And there's, I think, both room to make the interaction setting richer, but also room to do richer modeling on this setting and think about how does language convey things beyond just the context you're looking at? Okay. So the last project that I'd like to talk about is a negotiation game setting where language is explicitly used strategically. And this is the board game Diplomacy. So I was a postdoc at Meta at FAIR last year, and I was part of a team that built this agent called Cicero, which was a dialogue and strategy agent for this game that I'll show you called Diplomacy. This was a really big project. I'm going to kind of give you an overview of a small part of it that I was the most involved in. But I encourage you to, check out the paper or even other talks by other members of the team if you're interested in kind of the multi-agent planning and RL components of it. But so far, we've been looking at purely cooperative settings. And as a challenging testbed for approaches that we've seen, we'll look at semi-cooperative settings where the agents may not necessarily want the same thing in the world. So one motivation for this is theoretical from Nick Asher and Alex Laskaridis, where they say games which are subject to these Grecian principles that underlie all the games we've looked at so far, where agents want the same goal and what's the reward for one player is also the reward for the other. They're really just kind of a subset of all of human linguistic interactions. So in like a courtroom setting, or if you're haggling over a price for a product, there's going to be a distinction between being aligned rhetorically, where you want to get your message across, and being aligned strategically in what you want to happen in the setting. So we're going to need more sophisticated modeling there than what we've used before, and there's several different levels of cooperation. But diplomacy has also been identified as kind of a test bed for cooperative AI generally, because you want a system that's going to help you out and interact with you, even if your interests aren't totally aligned. So diplomacy is this board game that's been around since the 50s. It was actually John F. Kennedy's favorite game. And if you've played Risk, there are some similarities to Risk. You're one of like 7 European powers. It's set in World War I. And you're basically trying to get as much territory as possible. There's a couple ways to win. You don't have to take all the territory, and actually you almost never do. But you need to cooperate with other players and form alliances in order to have them support you in the game. So the way that you do that is each turn has 2 parts. There's first a natural language negotiation phase where you see an example here where like Germany will say want support to Sweden. England kind of says there are concerns about it. Germany makes some guarantees and promises. Then at the end of the turn, and all of these dialogues are private. So you're talking directly to one other player, but you don't see what that player is saying to others. Then at the end of the turn, all players are going to take simultaneous moves. So they enter their moves in. Those are all revealed at the same time. And you see whether the other person did what they agreed to do with you or whether they're surprising. And so obviously the agreements that people make are non-binding. So you have to build trust. You have to convince other players that you're good at the game. And you need to get them to help you out if you want to make progress overall. So to win this game, you both need to have strategy in the moves you choose to make, but you also need to be able to persuade other people and cooperate with them. So for these reasons, people have been interested in diplomacy for a long time, but past work only dealt with language-free variants, where you had sort of other signaling tools to convey your intentions to people, like restricted forms of communication. Any questions? It's interesting. I learned how to play this game during the last year. It's really hard. I found it really difficult, but it's a lot of fun too. Just don't play it with your friends because they say it's the game where friendships go to die. Yeah, I can tell stories about that if people are interested. But any questions? Yeah.
The questions I do not know. In the pre-negotiation phase, do you also have to choose who you're negotiating with, like for an agent?
Yeah. Yeah, so you get some of the problems of multi-party dialogue here too. And yeah, you do need to choose who to talk to. You need to choose how often to talk to them. And that kind of differs in various versions of the game, whether they're like speed rounds or longer term ones. But yeah, it's an interesting, we'll see a little bit about that in a sec. So yeah, so there's some challenges here are, it's a long horizon dialogue task. You need to send hundreds of messages with multiple parties. These messages need to kind of like be accurately grounded. You don't want to describe something that's wrong about the board because then people aren't going to trust you. Or if you do, maybe you want to, say why you made that mistake. But you also need to win the game, right? So you're going to be using language strategically, and you're going to be conditioning your strategy on what other players have said to you. And there's some tension between these goals, right? And we've kind of seen this tension in the other projects that we've looked at, where you want to produce things that are fluid and kind of like literally true, but you also want to bend those utterances or steer them to achieve the goals that you want. At a high level, we're training speaker models here to imitate people's behavior in context. So part of the reason that we worked on diplomacy is that there are actually a lot of people play this and play it really seriously. And there's this website called webdiplomacy.net where we used 50,000 games between people. Each game has 7 players in it. So there's a lot of data here. Hundreds of thousands, if not millions of utterances. The numbers are in the paper. And we're going to train speaker models that just kind of like give us proposal distributions for language in context. And the context here is, the board state, the past dialogue history, and we'll see some other things like strategy that we can condition on in a second. But there's enough data here, and pre-trained models are good enough that the language actually kind of looks convincingly human. So here's an example of a dialogue between a human who was England and our agent, which is France. This was an anonymous game, so we only told the human after the game that they were playing against an agent. But we had infrastructure problems. The agent actually went down for a while, and we were conditioning the messages on the amount of time since the last message was sent. So there was a big gap. And the model in this case learned that it could, like, from the training data, maybe it should say something like, I was on the phone with my girlfriend to explain that gap. And, the human kind of plays off of that. But there's limitations of speaker models. And we've seen some of those limitations before, the hallucination, lack of contextual independence. But I think an interesting one that applies to large language models generally is that these models are trained basically on average human behavior, kind of the mixture of, for GPT-3, all the text on the internet or whatever they trained on. But in this setting, the text from a wide range of human behaviors. So some players are very good, others are weaker. But if we just sample from a model trained on everything, we did like quality conditioning and stuff, but we still have these issues. You will kind of only get average human behavior. And we need to produce good descriptions of actions because that's how we get people to cooperate. So yeah, so we want to outperform humans, and we need to do that at a strategic level. So we'll decouple strategy, like choosing what actions and how to describe them choosing what actions from how to describe them. The approach that we use actually looks like a classic dialogue system in a lot of ways. So you don't worry about the details of this, it's in the paper, but I just want to show you that there's kind of 2 components. There's a strategy component, that's a language condition planner. See the paper or talks from like Noam Brown or Adam Lehrer for details on that. There's also planner-informed language, where we're going to condition the agent's language on the plans, like the actions that the agent selects. And we'll also reason about the effects of the agent's language on other players' plans. So the way that we'll try to decouple things, and I'll just go quickly through this, it's basically kind of like a distant supervision approach, where we are going to have representations that underlie the messages we send, which are the actions that the agent wants itself and its partner to take. So we have some noisy supervision for that. We have the actions that were taken at the end of the turn, but people can update their plans as they talk to each other. So we want to account for that in the annotations that we do. So they're called intents in the paper. They're basically, the action that would underlie the actions that would underlie the actions taken if the dialogue ended at this turn. So like supporting Belgium from the Netherlands, England's doing that. France is, who knows, it's underspecified. France says, no, I'm actually going to do this other thing. Now we have evidence about their action. And then England says, okay, I'll support you in. And then at the end of the turn, we get actual evidence of what they did. They could have been lying. We have to filter those out. But we're basically going to do model-based annotation where we predict the actions for each message. And then we can use that to train a conditional speaker model that gets access to those intended actions and produces the language, also conditioning on the board, context, et cetera. And when we have this factored model, we can choose the actions kind of arbitrarily and then describe them in a contextually appropriate way. So this lets us choose actions using this I didn't work on it, so I can say it's sophisticated planner that figures out kind of the equilibrium moves for both players, regularized towards what's been said would be likely in the text. We can choose the actions, and then we can hand those off to our dialogue model. And we can also choose, using approaches that we saw before, ways of describing these actions. We'll see more about that in a sec. But this allows us to kind of control what the agent says based on what it plans to do. So the same situation for both of these, but two different actions. In one of them, France is going to, the agent wants our human partner, France, to help us into Belgium. And when we feed in the actions that say this, the agent phrases it as a request, mind supporting Edinburgh to Belgium. Whereas if we instead are going to plan out that we're going to support France to Belgium, then we can phrase it as an offer. Let me know if you want me to support you to Belgium, otherwise I'll probably do this other thing. So the language model has some flexibility here. Like we aren't saying you should phrase this as a request or an offer. We're just kind of phrasing representing the actions that we want to happen, and it chooses between them. So I said this is the game where friendships go to die, and it is a semi-cooperative and difficult game. But the interesting thing is, at a high level, it's generally best to be honest. And part of the reason for this is that it's an iterated game. You're playing with the same partners over and over, and they'll learn whether they can trust you or not. But it's also just very difficult to recover within a single game after you've lied to your partner. So here's an example of this where we had a lie detection system, but in this case, it didn't work. And Turkey's our agent, it lied to Russia, and Russia just kind of gets unhinged and says, you lose until you repent, don't play me for a fool. So because it's hard to also plan about how to use kind of strategic withholding of the truth or lying, strong players use lying sparingly. So we had the agent honestly try to describe the actions that it plans to take. But there's considerations here. We'll implement this using, at a high level, something similar to what I showed you before, where we're going to consider different possible candidate messages, and we're going to evaluate each one for honesty and for strategy, and also just filter out mistakes. So we'll have a set of models. They're actually kind of complex ensembles of models, particularly for detecting grounding errors in this filtering ensemble. But at a high level, there's an intent predictor, the model we used before for annotation, and that's going to try to enforce honesty. So we'll feed in each message, and we'll see for the actions the agent intends to take, does the probability of those actions go up or down this message? If it goes down, we don't say it because it's probably a lie. We'll also try to be strategic. So this message is also true. I'll move to North Sea, but it reveals a little bit more that we're now allied with Russia. And maybe we don't want to reveal that to our partner because they're going to use it against us in this turn. So to deal with this, we'll use the same planner that we're using to select our own moves, but we'll hypothesize moves for all the players conditioned on this hypothetical message. And we have kind of an expected value model that says what's the resulting game state if players take the likely actions. And we see whether that predicted value increases or decreases based on this message. And we'll use that as another filtering criterion. And then we'll also just try to remove nonsense in the messages. So the class is over a lot of details, but just to show you kind of a success case of it working. So here's Cicero, the agent. Let's see, the screen turned off. Hopefully we're still okay. Cool. So Cicero is playing France here, and Cicero says, I'll work with you, but I need Tunis for now. And Turkey pushes back. This is the human partner. But the agent has kind of planned out good actions for both its partner and itself. And the language model is able to verbalize those actions, saying, you have Serbia and Rome to take. And Turkey says, no, I can't do that. And the language model, still conditioning on that plan, describes kind of the other elements of this action sequence. We're also proposing hypothetical actions a few turns in the future. There's details in the paper, but this convinces the human partner. They said, yeah, that's right. And then they continue to work together throughout the rest of the game. So we tested this out by entering this agent anonymously in an online diplomacy league. This was a lot of fun, both in the lead up to it and actually running, because, up until this point, we were kind of doing, filtering of the bad messages that the agent had, but we didn't want to have a human in the loop when we actually ran it. So we kind of took a risk in some ways. But the agent ended up, and we didn't tell people they were playing against an agent until after things were over. Because they would have thrown off the dynamics quite a bit. But the agent came in second. There's also, how do you choose when to stop the thing? You don't want to just stop when you're in first. So we kind of like pre-registered conditions ourselves. And interestingly, no player explicitly said that they were able to detect this as an agent, which I'd say is probably partly because of expectations, but also partly because pre-trained models are really good these days. So it played 40 games over 70 hours with 80 different human partners. But there's definitely room for improvement. And even though we tried to make the agent honest, just because of the nature of the game and limitations of our honesty detection method, it did still lie and backstab its partners at times. So they wrote about this in the New York Times. They also wrote on ChatGPT in this article. It was a pretty decent article. This is one person who we played against, and they said, yeah, the language seemed great. It also had this kind of like human-like behavior of lying to me and betraying me. So I think working in these kind of semi-cooperative settings is theoretically really interesting. We needed definitely more sophisticated methods here, not just because of the semi-cooperativity, but yeah, it's still a toy setting, and I'd encourage, thinking about like kind of what's the nature of the objectives in settings that you might work in. I'm definitely still very interested in cooperative settings. But yeah, we found, we've talked about all of this. You can do planning to kind of outperform the average people that you train your models on. We saw examples of that, and strategy and language can both inform each other. But to sum everything up, so language is this kind of cooperative process between agents. Those agents could be people, but they could also be a person and a system. And we found that we can improve language systems if we simulate how people act and use models of people to plan, and then collaborate better with actual people across all of these settings. So this work was joint with a lot of folks, including in particular Volkan and Ronghang, who helped lead the navigation stuff that I worked on, and Jesse, who did the flight pref data set. Jifu, who's applying to PhD programs this year, who did the image captioning work, and also the fair diplomacy team, which was a really large and fun team to work with. But yeah, thank you. I think we hopefully have some time for questions. It went a little bit longer than I planned, sorry.
Right, let's go through a couple questions.
Your team in Diplomatica has an advantage. So with comparison to human speaker, like the number of messages systems and communicate that with other people and so on.
Yeah, the first part was, did the Cicero agent have advantages over people? Yeah. So the message thing, it was able to send messages kind of, just limited by the GPU speed. And that's actually something we had to control, because you don't want to be, just spamming the other person. It would convince them that you're not human, but it would also just be confusing and more opportunities for mistakes. So we had a set of models which predicted when to generate messages. We actually had a domain shift because we trained those models on longer form games, like 20 games where you had 24 hours to make a turn. But then we evaluated them just to get enough, data to evaluate in 5-minute games. So they were much quicker. We had to kind of do posterior calibration of those models in order to get it to transfer. But yeah, that was one advantage. These models can adapt a variety of different styles too. So there was some work that Monet, who's one of Dorsa Sadig's students at Stanford, she did an internship project on style control of the models, which didn't end up making it into the final system. But one thing we did was prompting the model with kind of very verbose, polite, well-reasoned messages, just starting it off with that. And that led to it having a much higher chance of continuing to produce that kind of dialogue over the course of the game. Whereas if you just sampled from the model kind of unconditionally, you might get, very terse kind of even belligerent messages. So I think at its best, there's room to, produce these messages easily without having to think about and spend a lot of time doing it. But the intent control and the hallucinations are still big issues. Good question. Yeah.
Do you notice any differences in the variance between Cicero in multiple games or different settings and humans, or the ability to recover or adapt quickly to a bad turn choice or something? compared to like English.
Yeah, so the system is like way worse at that. If it makes, we had spirals. This was a problem for like months, where if the system like made a grounding error and the person it was talking to was like, what? That doesn't make sense. That's just most of the time off distribution for the model. And there was almost no recovering from that afterwards. So yeah, all of the exposure bias issues are pretty hard here. That was why it was scary for us to like turn off the message filtering. But you know, so one thing about these like faster settings is just the other person is expected, you know, shorter turns, the other person is expecting that their human partner is kind of going fast. So they're a little bit more forgiving of errors. So that helps too. But yeah, I think the system would not be ready to do the full 24-hour game for those reasons. A lot more time for probing. And things would totally change too if people knew it was a system. So the planning algorithm is designed to not be exploitable, but I defer to others for kind of details on that. But like the language would absolutely be exploitable. You could definitely, you know, put in adversarial examples and throw things off. Yeah, was there another? Yeah, Daniel.
For the nice talk. One question, maybe you said it yesterday. You mentioned that truthfulness or honesty was almost a strategy. But sometimes strategy lying was better.
Yeah.
As if you did not have that strategy lying, how that new model would be like the model.
Yeah, so I should clarify the model that we implemented actually was designed not to allow strategic lying. So it proposes kind of plans that it's going to take in the next turn, and it always attempts to describe those faithfully. So we didn't kind of like give the model an option to say something that it did not plan to do in the short term. The lies that it produces are either because the strategy changes over time, or because it just makes a mistake in what it's describing. So so unintentional lies, right?
Yeah, although there's sort of an implied commitment. You talked before about unless is quite about public commitments,
right?
And so there's an implied commitment,
Yeah,
and that's not actually what it means by it, but it's how it's interpreted.
yeah.
So this is actually a difference in a difference in the maxims that it's following as opposed to the maxims that it's thought to be following.
Yeah, that's a good point. Yeah, so that's one thing that would change if people knew it was you know, a fallible system. So I guess in theory, the planner that we have that conditions on a language should like in theory be able to like learn to adhere to public commitments, but it's trained on data that also has lies from people. That could be part of the reason, but it's, you know, a big part of it's probably just model failures too.
Yeah, has anyone been sort of looking at the games that have been played since you notified them that there was a bot?
We actually took the system down at the point where we notified people.
I mean, since then, you know, there have been cases where people have put chatbots up on the internet.
Oh yeah.
And things, and afterwards people are paranoid and are convinced that they're playing with or conversing.
Oh yeah, that's interesting.
Could anyone ever replicate this experiment not even at once? Do we have to go find a new game?
Yeah, that's a great question.
Actually, all games forever have been poisoned. Sorry.
Well, I hope that's not true. Yeah, I think it's a great question.
Maybe it's complicated enough that there's no benefit in thinking that your partner is an agent, but I don't know how it would change the dynamic exactly, but
Yeah, it could, and the system could definitely, or people could design other systems which would have different capabilities, different like degrees of trustworthiness or adherence to public commitments. But yeah, so it definitely changes. But there's also, you know, like a lot of variation in how people play the game. And a big part of the like planning that people have to do here, or sorry, the planning that the system does here, I didn't talk about it, but there's papers by like Athul Jacob that look at how can you kind of like, you need to like just have your actions adhere to human conventions, and people have kind of converged on those conventions in the game. And those conventions could change if the system gets introduced also. So, you know, there's a bunch of different just like stable things that you can converge to. And yeah, it could definitely change if the system doesn't adhere to those. We tried to make it adhere to human ones here, but yeah, I think it's a great point. This is kind of an iterated game on a longer scale too.
Okay, well, let's thank Daniel for a very clear and thought-provoking talk.